Now, once the capacitor is charged, it can maintain its charge because no more current is flowing through, right? The next thing we have to worry about is discharging the capacitor. Now, how do you discharge the capacitor? Okay, remember when we started talking about charging it? We moved the switch to position A so that the current could actually start to move. Yeah? But now, what happens if I don't, well, my current isn't flowing. In order to discharge this, I have to now connect this into my circuit. So this becomes irrelevant. Now my capacitor will start acting like the source of the EMF. Make sense? And if there was a light bulb here, it would turn on. So now how do our equations change? So ready to see that? Okay. So once fully charged, move the switch to B, to position B. Now, again, the question is, how does the current flow now? Okay, answer. Number one, capacitor discharges through resistance R. Number two, EMF is removed from the circuit. Oh, I probably should have done two first and then one, but it's okay. Which means our conservation of energy equation that we wrote as E equals IR plus Q over C will now become 0 equals IR plus Q over C. Now using the same thing as we did before, so nothing new, dQ over dt R plus Q over C equals 0. May I rearrange this to give me dQ over Q equals minus 1 over RC dt. There's a couple of steps in the middle. I expect you guys can do those, right? The only step that might be, so just do dQ over dt R equals minus Q over C. And just bring the Q to this side and R to this side and T to that side. Right? Because like things should be on the same side when we do integrations. Okay, what do I get? Now, may I integrate using the same boundary condition? That at T equals 0, Q equals Q naught, the maximum charge. What will my equation look like? Okay, so when I integrate this, what will I get? Integration 1 over Q dQ, starting from some initial Q to that, equals 1 over RC, integration dt, from some 0 to some time t. This will give me log of Q over Q naught equal 1 over RC t, or Q equals Q0 e to the minus 1 over RCT. Again, I'm going to use a different color for this. I'm going to use green. Here, the time constant is still RC. However, for the discharging case, it is the time when the capacitor charge reduces to Q naught e to the minus 1, which is equivalent to 37% of initial charge Q0. Again, Q as a function of time is great to know, but my fundamental question was, how does the current flow now? So how do I take my Q and go to I?
By dt.
What?
Put it over dt.
There we go. Can we do that? So I will just be dq over dt, or q naught d over dt of e to the minus t over rc. Very good. Which is also equal to e minus t over rc minus 1 over rc. Q0 divided by RC with a minus sign, e to the minus t over RC. And we can simplify it by knowing Q0 is the same as CV or CE. So I can rewrite this as minus E over R, e to the TRC. Now, what does this negative sign mean? This negative sign means that the current now is opposite to when capacitor was charging. Now, what will these graphs look like? So delta VC, delta VR, minus 10, and VC. I can never draw this properly, but it actually has to reach 0. In words, I can write this as delta VR, which is equal to IR, is negative, at t equals 0 and rises exponentially to 0. Whereas delta VC, which is defined as Q over C, falls exponentially from max value it had at t equals 0.